Hello everyone, myself Vaibhavi Solanki and welcome to my YouTube channel. So, today I am going to talk about Newton's laws of motion. Let's start. So, at first, the laws of motion are formulated by English physicist and mathematician Sir Isaac Newton. So, they are called Newton's laws of motion. There are three physical laws together that laid the foundation for classical mechanics. They describe the relationship between a body and the forces acting upon it and its motion in response to those forces. Most precisely, the first law defines the force qualitatively. Second law offers a quantitative measurement of the force, and the third one asserts that a single isolated force doesn't exist. It means that forces are always occur in pairs. Now we will discuss three laws in detail one by one with some examples. So the first law states that in an inertial frame of reference, an object either remains at rest or continues to move at a constant velocity unless acted upon by a force. So, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Here we take one example of a ball. Here we assume that the ball is at rest. Now, if we will apply some force from here, from left side, the ball is moving in this direction. It was not moving until we applied force on it. This first law is also known as the law of inertia. Here, inertia means that tendency of an object to resist changes in its state of motion. Here the object is ball, and as we applied some force, it will change its state. Mathematically, this law can be present as summation f is equals to 0 or dv upon dt is equals to 0. This only applied when the mass of object is a non-zero constant. Here dv by dt is acceleration a. There are two clauses or parts of the statement of the first law. One is that it predicts the behavior of stationary objects, and the second is it predicts the behavior of moving objects. The two parts are summarized in this diagram. When forces are balanced, acceleration is 0. When objects at rest, velocity is 0. Objects are stays at rest, while when object in motion, velocity is non-zero and objects stays in motion in same speed and same direction. So, the behavior of all objects can be described by saying that objects tend to keep on doing what they are doing unless acted upon by an unbalanced force. If at rest, they will continue in this same state of rest. There are many examples of Newton's first law of motion. Some are given here. First example is of basketball. When a basketball player shoots a jump shot, the ball always follows an arcing path. The ball follows this path because its motion obeys Sir Isaac Newton's law of motion. Now, second example is of car. The car remains at rest until some force applied on it. Here, this is stationary car, which means that there is no force applied on it and the car is at rest and it is not going anywhere unless something forces to it. Here, the second car, and it is not stationary but it is moving, and so it will keep going until something stops it, that is, until some force applied on it. The next example is of hammer. The head of the hammer can be tightened onto the wooden handle by banging the bottom of the handle against the hard surface. Next, when a car brakes quickly, the passenger will be thrown forward because inertia tries to keep the passenger moving. Bodies at equilibrium are balanced and therefore there is no acceleration. If all of the forces acting on an object are balanced, then the object will continue at the same speed or remain stationary. Here the object, there are two forces acting on it. First one is the weight or gravity, that is W, which is acting downward, and the second one is normal force acting upward direction. Here we can conclude that normal N is equal to W and net external force acting on it must be 0. Here the normal force is equal and opposite to the weight W. Now Newton's second law of motion. The second law states that the rate of change of momentum of a body is directly proportional to the force applied and its charge in momentum takes place in the direction of the applied force. This law is valid only for constant mass system. Mathematically, we can write this law as F is equals to dP by dt, where P is momentum, F is force. Also, P is equals to m into V. So, F is equals to dP by dt can be write as dmv divided by dt. As m is not a variable, we can write as m dv upon dt, and we all know that the rate of change of velocity is called acceleration a. So F is equals to m into a, where a represents the acceleration. The net force applied to a body produces a proportional acceleration, so F is directly proportional to acceleration a. And if a body is accelerating, then there is always a force on it. Acceleration means a measurement of how quickly an object is changing its speed. So, this second law can also be stated in terms of an object's acceleration. From this equation F is equals to m into a, we can say that in an inertial frame of reference, the vector sum of the forces F on an object is equal to the mass m of that object multiplied by the acceleration a of the object. In the first law of motion, we say that forces are balanced, but in this second law of motion, forces are unbalanced and the acceleration of an object depends upon two variables. First one is the net force acting on the object and the second one is the mass of the object. And acceleration is directly depends upon force and inversely depends upon mass of the object. As the force acting upon an object is increased, the acceleration of the object is increased. As the mass of an object is increased, the acceleration of the object is decreased. Because mass is inversely proportional to the acceleration. Now, some example of second law of motion. First one is the example of a truck and a car. As we all know that the truck is heavier than car, so the mass of a truck is more than the mass of car. And as we show that acceleration is inversely depends on the mass, so if we use the same force to push a truck and a car, the car will have more acceleration than the truck because the less mass of the car. Here the next example. The greater the mass of the object, the more force is needed to make it move, as force is directly depends on the mass. Next example. It is easier to push an empty shopping cart than a full one because the full shopping cart has more mass than the empty one. This means that more force is required to push the shopping cart. Now, Newton's third law of motion. This law states that to every action there is always equal and opposite reaction. It also can be stated as all forces between two objects exist in equal magnitude and opposite direction, and forces are always occur in pairs. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. One example is shown here. If one object A exerts a force Fa on a second object B, then B simultaneously exerts a force Fb on A and opposite in direction. That is, Fa is equals to minus Fb. Here, this minus sign, negative sign represents opposite direction. There is no cause-effect relation implied by the law. For that matter, the force on A by B and that on B by A are exerts at the same instant. Now, some example of Newton's third law of motion. First example is of a balloon filled with air. When air rushes out of the balloon, the opposite reaction is that the balloon flies up. Here, air rushes means that air goes down, which can be considered as action, and balloon goes up can be considered as reaction. The second example is of car. When a car traveling on a road, the tires push forward on the road, but the road pushes on the tires, and these forces are equal and in opposite direction. Next example is of rocket. As rocket move forward, some gases are explaining backward, and the velocity of gases are very high. Here explaining the gas is considered as action and rocket going forward considered as reaction. Here the rocket exerts a large backward force on a gas in the rocket combustion chamber, and the gas therefore exerts a large reaction force forward on the rocket. Next, the swimmer pushes again on the pool wall with her feet and accelerates in the direction opposite to that of her push. The wall has exerted an equal and opposite force back on the swimmer. Next example is of a boat. While rowing a boat, when you want to move forward on a boat, you pedal by pushing the water backwards, causing you to move forward. Here the force F is considered as action and force F dash is considered as reaction. Thank you for watching.